Hello all of you. Welcome to the 6th week of lectures on the course on analysis and modeling in chemical engineering. In this week, we'll learn about heat equations and analogous equations for mass transfer and momentum transport. Where do we begin with is when we have, like, let's say, a non-uniform system, then we can have a variation in the property or any property we are looking at along the volume of interest, right? Until so far, let's say when we looked at heat exchangers or evaporators, we assumed that the concentration everywhere is uniform. Same did we assume when we are doing the CSTR. Even for the case of PFR, we assumed that there was a radial mixing. So, the concentration was uniform in the radial direction, but not in the axial direction, right? We are going to depart from that assumption now and look at cases where we have the spatial variations in the concentration in addition to the temporal variation, that is with time, right. So, let us say to begin with, I am looking at a vessel now, which can be a reactor or anything else, and in that vessel, let us say in general you are supplying some heat and maybe you are doing some mixing, and as a result of that, the properties inside this vessel will not really be constant throughout, right. You can imagine when I am doing any kind of mixing, there will be regions which will be more mixed, which are probably near the impeller, and there will be regions which will be less mixed, which may probably things near the walls, which are far from the impeller, right. What we call in chemical reactors as dead zones and things like that. So, you will have a non-uniformity in mixing. So, that can give you a density variation or concentration variation in the vessel. In addition, when I am heating it, you can imagine that the heating can also never be uniform. So, you can have variations in property like temperature throughout the vessel. Let us say, for example, the temperature near the wall will be more affected by the surrounding than compared to somewhere in the middle of the reactor, right. So, in general, we need to have a framework where we can account for the spatial variations in the property in addition to the temporal variations. We did have this briefly in the case of a PFR, where we had the axial variations, but now I am taking a more general picture, and we will try to do a mass and energy balance where you have a general variation in the spatial coordinates x, y, z and the temporal variations in time, right. So, let us say in this vessel now again I can go back to the notion of control volume. So, let us say we have a particular point R, and I can draw a control volume around this point, and I can look at any property M for that control volume, which will correspond to the property at R, provided the control volume is very small. And now, if I zoom in this control volume, it may look like something like this, where delta x, delta y, delta z are the length of the control volume in the each direction, and of course, I want to make it infinitesimally small eventually, but now I am making it some finite value, and then we take a limit as we have done in the past of delta x going to 0, delta y going to 0 and so on, right. So, this is my control volume, and what we want to do is to do a mass and energy balance for this particular control volume, right. So, I have defined a coordinate system x, y, z as I have shown here, and I can say that there is a point that is surrounded by this control volume, and that point or this control volume corresponds to some spatial coordinates x, y, z. So, if I now define the coordinate system or the coordinates of the vertices of this control volume, in the notation of the coordinate system we have described, I can say that this corner may correspond to some coordinate x, y, z. I can as well put it at the center of the control volume, but it hardly matters, because in any case delta x, delta y, delta z are infinitesimally small in what we are doing, right. So, just for simplicity, I am saying that one of the corner vertices, that is my x, y, z, and then of course, I can allocate the coordinates of the other corners of this control volume. So, this one, for example, is in the x direction. for the same value of y and z. So, we have x plus delta x, y, z. This one, for example, is x plus delta x. This is along x and also along z. So, we have x plus delta x, y, and z plus delta z in there. And similarly, this point is x, y, z plus delta z. The y is 0 for this, that starting point for this. So, we start with y. But then we can also move in the y direction. So, this corner is x, y plus delta y, z. This is x, y plus delta y, z plus delta z. And this will be x plus delta x, y plus delta y, z plus delta z. This is diametrically opposite corner to x, y, z, and things like that. So, we can have kind of the coordinates prescribed for all the corners, and once we do that, then we can basically see this control volume as consisting of 6 faces, right. So, one of the face, for example, is this one, that is, you can say, kind of a YZ plane at x, and then we have an opposite face here, that is again YZ plane at x plus delta x, right. And now let us say that one of these planes I define as the input plane, where the input comes in the control volume, and other one I define as the output plane, right. So, in this case, I define this one as my input and this one as my output. So, the perpendicular direction of the YZ plane is my x direction, right. So, the flow or anything comes in the x direction, crosses this YZ plane and enters the control volume, and while it is going out, it is at the position x plus delta x, but still in the x direction. It crosses the YZ plane and goes out from this particular plane at x plus delta x, right. So, this is just a matter of convention. I am saying that x is input and x plus delta x is output. If, for example, if this is not true, then one of them is going to be negative. So, this one becomes negative if the outflow is going in that direction, and this can also be negative if outflow is in the opposite direction, right. Similarly, we can also define the planes in the xz thing, right. So, we have an xz plane at y, which can again be my input, and then xz plane at y plus delta y becomes my output. And then in a similar manner, we have another plane right here, that is my xy plane, that is my input, and then behind it on the other side, we have another xy plane at z plus delta z, that is the output, right. So, we can define basically 6 faces or 6 planes, one yz plane, one xy, and one xz plane becomes the input faces. So, 3 faces are input, and then 3 corresponding faces are output, right. And then we basically have mechanisms for anything to come inside the control volume and anything to go out of the control volume. And again, the convention that we have defined as in and out, it is just for simplification. If, for example, it is in the opposite direction, then whatever value we get is going to be negative, right. This is how we have defined the coordinate system in the present case. So, in that case, if I have to write the mass balance for this system, we can begin with some density of the fluid that is coming in, right, and that density is some rho, and rho can also be spatially and temporally changing, right. So, in general, it is not constant, right. So, rho is my mass per unit volume. For the input coming at the yz plane, if I multiply this rho with the velocity of the fluid, what exactly we get is mass per unit volume into the velocity, that is something like length by time, and length by volume, basically corresponds to this cross-sectional area that we have. And what is the cross-sectional area of this yz plane? It is essentially this delta y, delta z, right. So, what we have therefore is rho into Vx becomes essentially mass per unit time into area, and the area in that case is delta y, delta z. So, if I move it on this side, I get essentially a mass flow rate, that is mass per unit time, right. So, rho Vx coming at x into delta y, delta z, therefore comes the net mass per unit time, that is entering this control volume. Now, if I extend the same logic for the opposite phase, the output phase, again for this phase, rho into Vx defines the mass per unit area per unit time, and area again is delta y, delta z, right. So, we have rho Vx at x plus delta x into delta y, delta z, defining the mass per unit time, that is leaving the control volume at the opposite phase, right. I can also define the quantity that we have here, mass per unit area per unit time, as the flux, right. So, flux multiplied by the area gives me the molar flow rate. We can also think of it this way, rho Vx itself is the flux. If I multiply with the area delta y, delta z, we get the corresponding mass flow rate, right. That is what we are doing here. So, there is an input at x and output at x plus delta x. And just like whatever I have said in the previous slide, so now I can do the same thing for the 3 input phases and the 3 output phases. For example, again for this phase, the area of this phase is going to be something like delta x into delta z, and the flux now is rho into Vy. So, rho Vy at y multiplied with delta x, delta z gives me the mass per unit time entering the phase at y. And similarly, at y plus delta y, we have rho Vy at y plus delta y becomes the flux multiplied with delta x, delta z is the mass per unit going out in the y direction. And the same argument I can apply also for the phase right here, that is into the plane, into the slide plane I am showing here. This is the inflow, and outflow happens from the behind of this, right. So, this becomes my in, and at z plus delta z I becomes my out, right. And then I apply standard calculus whichever I have used earlier, but before that what I am doing, in minus out is equal to my accumulation. What is accumulation? Accumulation is the change in mass of the control volume. What is the mass of the control volume? It is density multiplied by the volume of control volume. What is the volume of control volume? It is delta x, delta y, delta z. So, if I multiply rho with that, that gives me the mass. So, dm by dt, that is how the mass of control volume is changing with time, that is my accumulation term is given by this, right. Recall the mass balance, in minus out equal to accumulation. That is exactly what we are doing here for the control volume. Keep in mind, for mass there is no generation, right. In this case, we do not talk about chemical reactions, but even if there is a chemical reaction, for the total mass, we do not have any generation. The mass is kind of conserved, we do not have a generation term. So, now if I divide it by delta x, delta y, delta z and take the limit delta x going to 0, delta y going to 0, delta z going to 0, then I can write this as something like this, minus the partial derivative with respect to x, rho Vx, that is my first term. Keep in mind that I have to put a minus sign in front to get the standard difference form for dou by x of rho Vx, and then similarly for rho Vy and similarly for rho Vz. And on the right hand side, once we divide by delta x, delta y, delta z, I am left with dou rho by dou t. These partial derivatives are very important. Okay, so this is the mass balance that we have derived here. And now I can write my velocity vector at any point, in this case x, y, z, as 3 components: the Vx component, Vy component, Vz component, and Vx component is along x direction. So I have defined a unit vector Ex in the x direction, and then Ey in the y direction, Ez in the z direction. So Vx Ex plus Vy Ey plus Vz Ez, where Vx, Vy, Vz are the magnitudes of the velocity components, and Ex, Ey, Ez are the unit vectors in x, y, and z directions. We can basically use that to write this mass balance equation in a vector notation or a compact notation. In order to do that, we also will define one operator, that is this del operator, and this del operator is essentially defined as this: the Ex unit vector in x direction dou by dou x plus unit vector in y direction dou by dou y, unit vector in z direction dou by dou z, right? And then I can simplify this as minus del dot rho v is equal to dou rho by dou t, right? It's not very difficult to see how it comes. Let me quickly show it here. So we have Ex dou by dou x plus Ey dou by dou y plus Ez dou by dou z, that is my del, and I have to dot this with rho and then Vx Ex plus rho Vy Ey plus rho Vz Ez, right? And now you see Ex dot Ex is going to be equal to 1, Ey dot Ey is going to be equal to 1, and Ez dot Ez is also going to be equal to 1. But every other dot product, let us say Ex dot Ey or Ey dot Ez or Ex dot Ez, all of them are going to be 0. So now if I do the dot product, I essentially will get whatever I had earlier. So in compact notation, I can write minus del dot rho v, that is divergence of rho v, is equal to dou rho by dou t, that is the time derivative, the partial time derivative of the density. Now in most cases the density remains constant, and in that case what we say as an incompressible fluid, where the density is assumed to be constant, I can take rho out of this because rho is constant, and then this term goes to 0 for the incompressible fluid, and then I get a rather simple equation del dot V equal to 0, which we know also as the continuity equation. If I want to express this in terms of the velocity components, this is going to be something like dou Vx by dou x plus dou Vy by dou y plus dou Vz by dou z is equal to 0. All right. So now we can go ahead and do the energy balance for this system. And again, we use the idea, we have used it before, that the energy coming in the system is essentially the enthalpy that is coming in the system, and energy which is going out of the system is basically the enthalpy which is going out of the system, right? But in addition to that, we can also have a net heat added to the system, that is Q, which I have used in energy balance of reactors. So we will have some net energy added, right? And I can express all of this in terms of fluxes. That's exactly what we are doing here. So rho Vx already was the mass flux, which was mass per unit area per unit time. And if I define this, if I multiply this with the energy per unit mass, then I will get energy flux, right? And energy we have replaced with enthalpy earlier, because H is equal to E plus PV, where E is the internal energy, and by doing that we account for the flow work in the system. The same argument I am going to use here. So mass per unit area per unit time, that is the mass flux rho Vx, into H, which is the enthalpy per unit mass. This gives me essentially an enthalpy flux or enthalpy per unit area per unit time. And again, if I multiply with the corresponding area, which is delta y delta z for this phase, that gives me the net enthalpy coming in the system with the fluid that is coming in. And what is that equal to? It is equal to rho v x multiplied with h at x multiplied with delta y delta z. And similarly, for the opposite phase, I am going to have rho v x into h at x plus delta x into delta y delta z, right? And I can apply this argument for all the three phases, whatever I have done for the mass balance. So, for the y direction, I am going to have something like this, and for z direction, I am going to have something like this. In addition to this, I am also adding heat, and the heat that I am adding, I also want to express in terms of heat flux, right? So, this is basically heat added per unit area per unit time, and this again has to be multiplied with the same area, which is delta y delta z for this particular phase. So, qx at x into delta y delta z gives me the heat input at x, and then I subtract the heat output at x plus delta x. And similarly, I can do for the y direction and I can do for the z direction. So, I basically have considered the enthalpies that is coming in with the flow and the heat that is added to the system. I ignore the work which is done by the viscous stresses, right, in this system, or any other kind of work apart from the flow work, right, that is already accounted for in the enthalpy. We ignore all those work, and we also ignore typically the kinetic energy and potential energy for the systems that we care about. These are typically negligible, but if they are not, then it has to be considered. So, this is going to be equal to the energy accumulation. So, the left hand side again is my in minus out of the energy, and that is equal to the energy accumulation. What is the energy of a system? Energy of a system is given as something like rho into h, which is the energy per unit volume. Why is that? Because rho is mass per unit volume and energy h is enthalpy per unit mass. So, it becomes enthalpy per unit volume, and if I multiply this with the volume of control volume, that is delta x, delta y, delta z, I basically get the net enthalpy of the system, and d by dt of that gives me the accumulation of the energy in the system. Okay, so I will have then expression for this energy balance. So, I have simply written this equation whatever we have derived, and I divided by delta x, delta y, delta z, whatever calculus I have done it for the mass balance. I am doing something very similar in this case, and then what do I have is dou by dou t of the rho h, that is my accumulation term that is coming from here, right. Keep in mind it is dou by dou t, the partial derivatives, right, because now I am applying over the entire system, right. So, when I was doing it for a control volume, I can use d by dt as well, but in the end I want to apply it for the entire system or a continuous variation for the entire vessel. So, therefore, I use dou by dou t here, right, and that is equal to, I can do a similar kind of thing. So, keep in mind this is rho Vx here, rho Vx here, this is rho Vy, rho Vy, and this is rho Vz, rho Vz. So, essentially we had the mass flux into the enthalpy per unit mass in the previous slide, right. So, I am using the same expression whatever I have here. So, I have missed Vx, Vy, Vz in the expression, right. So, that gives me in the compact notation the divergence of rho Vh minus the divergence of the flux vector, heat flux vector q, and then I can expand the first term, right, pretty much by what we do it for a typical derivative, d by d, let us say z of x y I can write it as something like x dy by dz plus y dx by dz. I am doing something similar here, but for the derivative del, right? And we have to be slightly careful when we are doing that. So del dot rho v is a vector and h is again a scalar. So only v is a vector here. So let us say I want to separate this part and this part. Then I can apply something similar to the above. So I will write the first term as rho v, and I could do del dot h, but h is a scalar. So I cannot dot it with a vector operator. Del is a vector operator. Therefore, I will use del h. This is my gradient of h, right? So I apply a vector operator del on a scalar quantity. So I get a vector now, and this has to be now dotted here. Of course, you can derive it by expanding it, but just I am giving you a hint what exactly we are doing. We have to just use our intuition of where to put the dot, right? I could have written del dot h here, but that would not make sense because h is a scalar. A scalar quantity cannot be dotted with a vector, right? So therefore, I have written del h, that is my operator applied on the scalar quantity h that becomes a vector, and then I have rho v on the which is left out. So I must do a dot product here to get a final quantity which is again a scalar. Energy is a scalar quantity. Now I will do take h out of this, and then I do del, and now rho v is a vector, so I can very well do del dot of there, right? You can expand these terms here if you wish. So in this case, del h is the application of del operator on h, that will give me ex dou by dou x plus ey dou by dou y plus ez dou by dou z applied on h. So this becomes ex dou h by dou x, ey dou h by dou y, ez dou h by dou z. So we will essentially get a vector quantity del h, right? And del dot rho v is whatever we have seen earlier, right? So just be careful in expanding it, and whenever you have doubt, you can always expand and see that whatever expression I have got here is indeed correct. So going forward, I will make the same assumption whatever I have made in the continuity equation, that will assume that the density is constant, that is uniform composition in space as well as time, and then I can take rho out of here, right? And I get something like this. And now you note that from continuity equation, del dot v is equal to 0 for incompressible system when the rho is constant. And then I get a rather simple expression right here because second term drops out from this expression. Going forward, I am going to use the notion that enthalpy in principle can be dependent on pressure, but we can ignore it for most liquid systems. And the enthalpy can change because of either a sensible heat change, that is something like Cp delta T kind of change, or as a phase change, that latent heat change. In most cases, we are interested in only the sensible heat change, right? And if we are looking at only sensible heat change or no phase change, and further if I assume that H is the Cp is essentially constant, it is not dependent on temperature, then enthalpy at any temperature T can be written as some standard value of enthalpy that is constant at Tr at reference temperature Tr, Cp into T minus Tr. Tr is something like standard like 25 degrees Celsius. So if I apply del on this first term will be 0 because H naught is a constant, and second term will give me Cp del T because Cp is assumed to be constant, right? So we assume constant heat capacity. So I can replace del H with Cp del T, and dou h by dou t as Cp dou t by dou t. Keep in mind, this is only valid when the heat capacity is constant and there is no phase change, and in that case we get something like this. And finally, now we have to ask ourselves how the heat is getting added in the system, and if it is by conduction, then we have an empirical relation known as the Fourier law that is valid in most cases. And that Fourier law tells me for the conduction case that the heat flux is given as something like minus k, that is conductivity, into del of T. And if I plug it in this equation, I am going to get something like this. So basically I have moved this term to the LHS and I will get this. And if I look at this del dot q, so minus del dot q is minus del dot minus k del t, and k, if it is constant, this gives me k del square t, where del square is defined as dou 2 by dou x square plus dou 2 by dou y square plus dou 2 by dou z square. It is called Laplacian. It is a scalar operator, right, that is applied on the scalar variable temperature, right. So del square T is going to be, I will put T in all of that, right. And this, what you see on the left hand side in the bracket, this is what is known as the substantial derivative, typically represented as capital dt by capital dt, right. You can read in transport phenomena the meaning of a substantial derivative. It depends on the choice of reference frame. So if you are putting a reference frame that is flowing with the fluid velocity, then the change you observe when you are moving with the fluid velocity is what is known as a material derivative or substantial derivative, right. But in all we care right now, it is this expression that I am representing by capital dt by capital dt. Okay. So now we have got what is known as the heat equation, that is for the conduction problem, and with whatever assumptions that we have made so far. And I can also write it as something like this if I combine k by rho Cp as some constant alpha, which is also referred in literature as thermal diffusivity. And as you may guess, the diffusivity word is also used in mass transfer. So there must be some analogy of this relation, heat equation, with the mass transfer equation. And indeed there is. We also know for diffusive mass transfer, unless there is an external agent and all that, we have something like this coming from the Fick's second law. And if you look at it, these two are very much analogous to each other. If I replace T with C and if I replace alpha with D, I will get essentially the same equation. What this means is whatever mathematical apparatus we develop for heat equation can also be applied for the diffusion equations, right. And the analogy is very similar to the spring dashpot analogy that we discussed in the beginning of the class. In fact, the same also applies for momentum transfer with a small catch, that is now the variable is a vector velocity. For heat and mass transfer, the variable is a scalar, temperature or concentration, but for momentum transfer the variable is the velocity, but I can still define a quantity nu, that is viscosity by the density, that is called the momentum diffusivity, analogous to the mass and thermal diffusivity. But there are some assumptions here. For example, in the actual equation, that is the Navier-Stokes equation, we also have a nonlinear term of this type, it is called the convective term, and we also have effects of pressure gradients, right. So if we ignore that, then we get something similar to this. But momentum transfer is going to be somewhat more complicated than compared to heat and mass transfer, because the fundamental variable there in the momentum transfer is the velocity, which is a vector, as opposed to scalar concentration or scalar temperature for the heat equation and mass transfer. So with that, I am going to conclude the derivation on the heat equation. In the next lecture, we will apply this idea on some specific problems. Thank you.